Okay, we're continuing on here, chapter 2. Still. All right, so last time we got into really significant figures, and we talked about significant figures in calculations. So remember that if you multiply or divide, you are looking at significant figures, and your answer should have the same as the least number of sig figs. So whatever the kind of lowest number of significant figures in your calculation on whatever number that may be is really the one that determines how many significant figures your answer should have. We talked about adding and subtracting, and remember when we add and subtract, we're actually looking at decimal places. And it also is the least number of decimal places. And again, that is what your answer should have. So um, sometimes people just kind of roll with sig figs on everything because that's like in their head. But remember, though, if you are doing some type of adding or subtracting, you do need to look at decimal places. The least number of decimal places is what your answer should have. That may give you a number that has a certain amount of significant figures. That may be important if you then maybe go on and use that in a multiplication or division type situation. Remember, as we talked about rounding. We never want to do any type of extreme rounding. We do want to make sure that we round appropriately. So again, 5 and above, we kind of go up. Less than that, we kind of drop, or may need to add zeros in certain cases, like we talked about. We want to end up with the right number of significant figures. And again, if you do multiple steps in the calculation, you definitely should avoid rounding to the very end. You should keep track of all your steps and sort of, where you should end up. Because again, as we saw maybe on a couple of those last time, it could actually just be the first step that you did in terms of the math that really ultimately determines where you should end up at the end, even though maybe at the end you're adding and subtracting, maybe at the beginning you multiply and divided. But that kind of first one might actually be the one that determines where you should end up. Remember as well, like I said, you will not always get the answer on your calculator to the correct number of significant figures. So remember, you do need to adjust it. And like I said, sometimes you may need to add zeros. You may need to get rid of numbers to maintain it along the way. Remember that if we have 12,000 and we have 12, they both have two significant figures, but a very different meaning in terms of both of those numbers. So again, don't do any of those weird rounding stuff. Any questions on sig figs, calculations, all that stuff? All right, then we're going to continue on. We're going to pick up here, I think. We're going to talk about prefixes and equalities. And we're going to get into sort of conversion factors and dimensional analysis and problem solving. We saw some prefixes earlier on, I think, in this chapter. And prefixes are used to sort of change the meaning of some numbers. It's used a lot with metric sort of units, like kilo, milli, and so forth. And an equality is also something that we talked about. An equality is two values on different units, scales, but represents the same amount of something. So for example, if we have a kilometer, that is the same as 1,000 meters. That again is an equality. They both represent the same amount of distance or length. 1 millimeter is the same as 0.001 meters, also an equality. 1 foot is 12 inches, also represents the same amount, also an equality. And we use equalities, as we will talk about, to write conversion factors. And conversion factors are used to help us really do problem solving. And really, from any equality that you have, as we'll talk about a little bit later on as well, you could really write two conversion factors for any equality. And basically, a conversion factor is really just a fraction. So, for example, if we took our 1 kilometer is 1,000 meters, that again is our equality. We could write two conversion factors, 1 kilometer over 1,000 meters, or we could write 1,000 meters on top and 1 kilometer on the bottom. And again, these are our conversion factors that we can use in a problem. As we will talk about, we will not use both of them in the problem. We probably just use the one that we need. But these are technically two conversion factors that are available to us to use to solve a problem. But before we get too far into conversion factors and equalities, let's again sort of touch upon those prefixes that I think we saw a little bit of earlier on in this chapter. Now, for example, when you have a prefix like kilo, it does mean 1,000. And as we see there, it doesn't matter what the base unit is. The conversion is always the same. Now, when we talk about sort of prefixes, we sometimes can refer to it as like a prefix unit. And those are all the ones here that obviously has, in this case, kilo in it. The base unit is the unit that you see in both sides of that equality. So kilometer, we see meter, and we see meter over here. The meter there is our base unit. Just like if we go below it, kiloliters are prefix unit, and we see liters really on both sides. That is our base unit. Kilogram and grams, grams being really the base unit here, and obviously kilograms being our prefix unit. Again, from any of those equalities, you could write two conversion factors for it. But sometimes people think, if you take something like kilo and you switch like base units, you go from like kilometers, or then you have kiloliters, somehow it changes. It doesn't. As you can see, the conversion there is the same regardless of what the base unit is. For one of the prefix units, there's 1,000 of the base units in each of those things. Here's a common sort of table that you see in your book. And these are different prefixes. So we have tera, which is 10 to the 2. We also have numerical value. I would say in most cases, these two sort of columns are very commonly seen together. Giga is 10 to the 9. Kilo is 10 to the 3. Again, I would say definitely kilo pops up a lot. Deci, centi, milli. So, this whole spot right about here pops up a lot. And picometers as well, 10 to the minus 12. So when you see these prefixes, again, it's really important that you use them correctly. And it is a super common error that people, when they go to a table like this, will always use these conversions really backwards. And they kind of don't use them correctly. So let's take a moment here and really talk about, how we could kind of use these correctly. So let's go back here, say the kilo. And kilo is 10 to the 3. So on a lot of these sort of prefix tables, you will usually see something listed like this, kilo, and next to it, it will say 10 to the 3. And when you see 10 to the 3, that is in scientific notation. And really, what that represents is 1 times 10 to the 3. So if you needed to put that into your calculator first off, you would put that in, like we talked about, scientific notation, and that is the kind of the number that you would put into your calculator. You would hit something like, on most people's calculators, maybe 1, your exponent button, and then 3, obviously, right? Again, when you hit that exponent button, it represents the times 10 part. So just like you're doing a scientific notation. Some people's calculators, you may even not even need the 1. You could actually maybe just hit the exponent button and 3, and it will probably work for you. It depends on your calculator. Now, all of that is these guys. This would be 1 times 10 to the 12, 1 times 10 to the 9, 1 times 10 to the 6. So when you see this column, 1 times 10 to the minus 1. So these are all 1 times whatever that exponent is. And again, if you need to punch that into your calculator we talked about, you would definitely want to make sure you're using your exponent button. So if we go to kilo, which is again is 10 to the 3, what that represents is, let's say we were doing, like we saw there in that slide, kilometers and meters. Once again, in this particular case, the kilometers is the prefix unit, the meters is the base unit. Now, where people always screw up when they go to do this conversion is they look on the table, they see kilo, they see 10 to the 3, and they decide, oh, that must mean 10 to the 3 to one of those. And then you get one of those because that is incorrect. So that is the wrong way to use that conversion. So when you go to the table and you see this, that is how much there is in the base unit to one of the prefix units. So what that means is if I have 1 kilometer, there would be 10 to the 3 meters. And that is the proper way to do that. I can't tell you how many people will do it the other way I crossed out there and kind of always go backwards on it. Once again, like we saw in that last slide, it doesn't really matter what the base unit is. If I had 1 kilogram, that would be 10 to the 3 grams, or 1 times 10 to the 3 grams. And that is the proper way to do that. Those are the equalities there. Once again, it doesn't matter if you come over here and we find milli, which is our little prefix there. And if we had milli, which says 10 to the minus 3, that would mean in 1 millimeter, there is 10 to the minus 3 meters. In 1 milliliter, there would be 10 to the minus 3 liters. So it is always, when you see that 10 to the 3, 10 to the minus 2, that is how much there is in the base unit to just one of the prefix units. And again, like I said before, super common. Everybody always wants to kind of reverse those and kind of use it incorrectly. First off, any questions on that there? So for example, we'll take that one there. We'll do milli, which was 10 to the minus 3. So we have milli, right, which is 10 to the minus 3. And let's just say, for example, we had 125 millimeters, and we wanted to know how many meters that would represent, right? So how should we approach this? We should approach this by just looking up there and going, milli is 10 to the minus 3. This will give us our equality that we could use. So once again, that would mean in one of the prefix units, which is millimeters, there is 10 to the minus 3 of the base unit, which is meters. And again, that's like your prefix unit, which should always be 1 when you're using the sorted table. And this is your base unit. And again, the base unit is the one that's in both of those numbers, basically, or both of those units. This, again, as I mentioned, is an equality. So, for example, as I mentioned earlier, from any equality, we could actually write 2 conversion factors. So on this particular one, we're just going to write 2 fractions. So we could say 1 millimeter on top is 10 to the minus 3 meters on the bottom. Once again, that is 1 times 10 to the minus 3. If you need to punch it into your calculator in scientific notation, that is what that represents. Or we could have a conversion factor where we basically just flip it. 10 to the minus 3 meters is 1 millimeter. These again are conversion factors. And you can always basically get 2 conversion factors from any equality that you come across. Now, which one should we use? Well, in chemistry, the way that we show our work is, as we'll talk about a little bit later as we continue on, but to sort of preview it for you, we show our work which was known as dimensional analysis. And dimensional analysis is basically using conversion factors and getting rid of units we don't want and ending up with units that we do want. And the nice thing about dimensional analysis, besides the fact that that's the way you should show your work, is as you get the hang of doing these type of problems through dimensional analysis, a lot of times you may not even need to worry about a formula or how to rearrange a formula. If you just know, like, I don't need those units, but I need those units, you could kind of take a dimensional analysis approach a lot of times, and it kind of does the rearranging of formulas for you some cases. It will also do the math for you. You don't have to worry about, did I do the math right, or am I doing the kind of the right math? So it really is really beneficial to do so. What is the idea of dimensional analysis? The idea of dimensional analysis is basically this very simple concept. Opposites cancel. So if you want to get rid of certain units, you need to put the exact same units in the opposite location. Now, what are our locations? Well, since we're using conversion factors, which are basically fractions, it's very simple. There's a top and there's a bottom to a fraction, right? There's something on the top of the fraction, something on the bottom of the fraction. And that's what we're looking at, and that is how you should set it up. So, for example, you would start with our made-up problem here of 125, and we're going to start with that number. I know for sure I do not want to end up in millimeters. I want to end up in units of meters, right? So, although this is not really written as a fraction, you could kind of make a fraction if it's easier for you to kind of visualize what's going on by just simply assuming this is over 1, basically, right? So now the benefit of maybe doing that is when you do dimensional analysis, you definitely want to keep the top on the top units and the bottom things on the bottom. We want to keep them really separated from each other. So by doing this, this makes it really easy for us to choose between my 2 conversion factors here. So I have a choice of this conversion factor here or this conversion factor here. Which one puts millimeters in the opposite location? Yeah, the one on the right, correct? So this is what I should choose. I didn't really have to think about other than opposite location, right? So very simple. We're going to put a millimeter on the bottom and 10 to the minus 3 meters up on top. And at this point, the other really nice thing about dimensional analysis is you will always know what math you're going to do. So when you set it up like this, no matter how, everybody on top always gets multiplied. So whatever's up on top gets multiplied, and whatever you got on the bottom gets divided. So whatever's on the bottom gets divided. In this case, we only got one thing on top, one thing on the bottom. But if I have 3, 4 things, doesn't matter. Everybody on top gets multiplied. Everybody on the bottom gets divided. That keeps the math pretty simple as well because I know exactly what I should be doing math-wise. And again, this can also help you when you get into some formulas that you don't have to worry about, did I rearrange it right? Am I multiplying when I should be dividing or dividing when I should be multiplying? That's what you want to do. Now, how does this actually work? Well, what's going to happen to our units is this. The millimeters on top and the millimeters on the bottom are actually going to cancel each other out. And it is no different than if I to ask you, if you had 4 divided by 4, what does that equal? 1. Same on the top, same on the bottom, equals 1. If I have 2 divided by 2, it equals 1 as well, right? So it works the same way with units. What we're essentially doing is taking millimeters on top divided by millimeters on the bottom. Those guys cancel out to 1. So that is the idea of the opposite location. When you put those units you don't want in the opposite location, you're essentially dividing them out and making them 1 and essentially getting rid of them. Any questions on that there? So now that I know those guys are gone, that leaves me only 1 unit, which is up on top, which is really good because if you are solving for a unit, 1 unit only, that unit should always end up on top. It should never end up on the bottom if it's just 1 unit. So that unit should always end up on top. Now all I have to do is actually just multiply it, right? So I'm going to take basically my 125. I'm going to multiply it by, again, 1, my exponent button, my negative button, and 3, right? That's the proper way perhaps to punch it in. And if you do that, you will end up with 0.125 meters in this particular case. Yeah. First off, any questions sort of on that setup? So it's a good question about significant figures. So let's talk about a little bit of significant figures here. What we are using here in this conversion factor came from this equality. And this equality is a metric to metric conversion, which means it falls under exact numbers, which means you don't have to worry about the significant figures there. So if you're using any type of conversion factor that is like a metric to metric conversion, a US to US conversion, they are considered exact numbers, which could have unlimited number of significant figures. The good news is you don't have to worry about the significant figures there. That means that the only number in this problem I should worry about is the original number here, the 125, right? Which has 3 significant figures. And that means that this guy should have 3 significant figures in terms of our answer as well. Now, the other nice thing about dimensional analysis is the only math that you do is multiplying and dividing, which means you are always looking at significant figures. So it keeps that pretty simple as well. You're only going to be looking at those least numbers of significant figures. Other questions? So why don't you try one? Let's take a look here. Let's grab, let's do nano. So let's say nano is 10 to the minus 9. And let's say that you had, let's say you had 484 nanometers, and you want to know how many meters that would be. So why don't you figure out the conversion factors you could use? Why don't you set it up dimensional analysis like we were just doing and see what you end up with there. You do need to show the dimensional analysis part, kind of the last part of the calculation. So ultimately, right here is kind of what you need to kind of show, yeah, in terms of the work. If it helps you to kind of write out everything else, you can. You don't necessarily have to on a quiz or an exam, but definitely the bottom part there with the setup is kind of what you need to show. It's in the circle. What's that? Let's see. So let's take a look at it here. So obviously here we got nanometers and we want meters. We probably want to go to the table there and find nano. And again, that nano is going to say 10 to the minus 9. And we want to make sure that we do use it correctly. So once again, that is how much there is in the base unit to one of the prefix units. So in one of the prefix units, which is nanometers, there will be 10 to the minus 9 meters. And again, that's going to be your equality here. That always is going to give you 2 conversion factors that you could use. And really don't overcomplicate it. It's just 2 fractions. Put one thing on top and then put the other on the bottom and then flip it basically. So 1 nanometer on top, 10 to the minus 9 meters on the bottom, or 10 to the minus 9 meters on the top, and 1 nanometer on the bottom. Once again, these are your two conversion factors that you can kind of choose from. So now that you did that, you definitely, as we've been talking about, want to kind of set it up so you can kind of see those units and everything is clearly top and bottom. So you could do that opposites cancel. We're going to start with the number that was given to us. So 484 nanometers. You don't have to do this, but it just helps you visualize it, put it over one so you can kind of see the top and the bottom and visualize what's going on. Once again here, we know we want to get rid of nanometers. So it really does make hopefully our choice easy. We want our nanometers to be in the same location or opposite. Opposite, which again in this case would be the one on the right? So that's the one we're going to use. We do not use them both, otherwise you undid your calculation, so you should only use one in the calculation. We're going to put the 1 nanometer on the bottom, the 10 to the minus 9 on top. Remember again, the 10 to the minus 9 is 1 times 10 to the minus 9, right, in scientific notation. Now, because I set it up in dimensional analysis, I automatically know what math I need to do. Top gets multiplied, bottom gets divided. 100% of the time, always when you set it up like this, there is no second guessing. You just know that is what's happening. In this case, the nanometers on top and bottom are going to cancel. We're going to multiply 484 times basically 1 times 10 to the minus 9. Once again, we want to make sure we use our exponent button like we talked about in scientific notation. That EE button, EXP button, whichever one you got going on there. That's a lot of zeros. I think I got them all. And it would be meters, as that is the only unit left. You could clean it up a little scientific notation, perhaps, with some less zeros. 4.84 times 10 to the minus 7 meters, yeah? In terms of significant figures, once again, I am not going to worry about that as that's an exact number. We come back to our original number here, which had 3 significant figures. And our answer has 3 significant figures as well. Yeah? Both answers are correct, yeah. As long as I put the right number of zeros there, I think I did. Yeah, along the way. Again, on my calculator, I got all zero. I got the non-scientific notation, which again you probably might get, but you can't write in scientific notation. Do you have a question? Yeah. So remember though, as we talked about with scientific notation, if your calculator gives you something like 4.84 e minus 7, that e does represent the times 10 part. So when you're writing the answer, you shouldn't use the e. You should turn it back into times 10 to the minus 7. Yeah. But your calculator may give it to you as the e, and that represents that. Yeah. Let's do this one here. Let's try. Let's say we had. Let's try this. Let's say we had something. We got something, maybe. I don't know. We still got something. Let's try. Let's do 1,432 microliters to milliliters. That's a double prefix shot there. I don't know if I like it. We'll see. I'm sure you'll like it. So micro is 10 to the minus 6. Milli is 10 to the minus 3. See what you come up with. By the way, your book likes to use micro, lots of different symbols. They use like MCG or something like that. Some weird symbols sometimes. Yeah. No, it's actually microliters. That's just, yeah, it's a symbol for microliters. It's like this weird kind of almost U-looking thing. Although, like I said, your book will actually use a couple different uh, symbols for it. They'll use like MCG, I think, sometimes for it. It's kind of weird. I've never seen it anywhere else besides that book, but yeah. So this is micro here. Correct is milliliters. Yeah. Here, I'll make the U a little bit longer that way. In a conversion from one prefix to another prefix, right? So in this case, we're kind of going from a prefix to a prefix unit here, right? And in this particular case, sometimes people want to do it all in one move, right? So maybe they want to figure out like how many decimal places need to move. They're singing that song about a king or something. I don't know. But probably shouldn't do that because you probably will get it wrong. Besides the fact you do need to show your work, not just moving decimal places and stuff like that. So what we want to kind of think about is why don't we just do like two conversions? And the unit that really ties both of these together, the base unit that ties both of these units together is what unit? Liters, right? We got microliters and we got milliliters. So the kind of base unit that ties both of these together is liters. And what I would recommend is you should take it back to the base unit. And then from that base unit, you should take it to the next prefix unit. Why should you do that? Because you probably will have this table given to you, and you could find those conversions super easy, right? Without having to figure out how to go directly from one to the next, right? So that is really probably the good approach. What we want to do is take it from microliters to liters, and then from liters down to milliliters. So all this is two conversions back to back, basically. We could still do a dimensional analysis. We could still do it all in one calculation if you want. You could even do it in two calculations if you want, however you feel more comfortable. So we're going to start with just the first part here. We're going to go from microliters to liters. So that means I go to my little table and I find my micro conversion, which says 10 to the minus 6. I know now that that means in 1 microliter, there is 10 to the minus 6 liters, right? Or 1 times 10 to the minus 6. That is going to give me my equality. That will give me my two conversion factors of 1 microliter over 10 to the minus 6 liters, or 10 to the minus 6 liters over 1 microliter as my conversion factors, right? All right, so we're just going to start like we did the other problems. I'm going to take my 1432 microliters. Again, if it helps you, put it over 1 so you can see the top and bottom location. Now I don't have much thinking to do, hopefully. I want to get rid of microliters, right? So once again, opposite location is going to do that. So I'm going to use that as my conversion factor. 1 microliter, 10 to the minus 6 liters. I also know that on top I'm still multiplying, right? And I am still dividing. If I stop my calculation right at this point, what units cancel? The microliters cancel. I am left now with liters, right? And because I set it up like this properly, there is no doubt where my liters are at. My liters are up on top, right? Which means if I want to get rid of them, they need to put them on the bottom. At this point, you do have an option. You could get an answer and then continue on with your calculation, or you could just continue on with the calculation. So I'm going to continue on with the calculation. I now need to do the second step, right? Which is liters to milliliters. So that is going to now take me to my milli conversion. And I know that milli is 10 to the minus 3, which means 1 milliliter is 10 to the minus 3 liters, giving me my equality I could use for my next part of my calculation. And that gives me my two conversions, 1 milliliter, 10 to the minus 3 liters, are 10 to the minus 3 liters up on top and 1 milliliter on the bottom. So if I continue on without getting an answer, I'm just going to put another little bracket there. I could clearly once again see liters are up on top. So to get rid of them, should I use the conversion factor on the left or the right here? The left has liters on the opposite location, right? So we're going to go 1 milliliter, 10 to the minus 3 liters. At this point, you may be wondering, math-wise, what do I do? All you have to remember is everything on top gets multiplied. So I'm still multiplying on top. Everything on the bottom gets divided. And when I divide that, liters on top and liters on the bottom go away. The only unit left standing is milliliters up on top, which is what I want. I got nothing left to go because that's where I want to end, right? So I'm going to take 1432. I'm going to multiply it by basically 1 times 10 to the minus 6 up on top, right? Again, making sure you use your exponent button. I don't really need to multiply by 1, but if you want to, I guess you could. You're going to hit equals. That's an important move right there. Make sure after you're done multiplying the top, you hit equals. Yeah. Now I'm going to go to the bottom. I don't really need to multiply by 1, but if you want to, you can. You can hit equals. I don't need to multiply by that. I do need to multiply by that number on the bottom, and that is 1 times 10 to the minus 3. So I'm going to divide it by 1 times 10 to the minus 3, put in my calculator properly, and I'm going to end up with 1.43 milliliters. This particular case, yes. First off, any question on the setup or the calculation? Yeah. Okay. Congratulations. I don't know. By different, what did you?
1.3 liter divided by 1, and then 1 over 10 negative 3, and then it's like calculating.
If you're asking like how you put it into your calculator, if that's what you're asking. So this is really the only way you could do it correctly is this. The only difference could be, for example, where it says 1 milliliter over 10 to the minus 3 liters. That's the same as 1 liter is 1,000 milliliters. We'll give you the same conversion, so you could use that conversion as well. So ideally, you got to kind of have sort of those conversions for it to technically come out right, but maybe it is. All right, let's talk a little bit about significant figures. Yeah. Yeah, there are different ways that you could do it. You could, yeah. So I would highly recommend for most people not to go straight, because most people, frankly, screw it up in most cases. And you do have the kind of table or conversions given to you that allows you to go to the base unit, and that would be the way that I would recommend to do it. There are, again, a couple different ways you do it. You can find the conversion that is between micro and milli and use that, and you still need to set it up the dimensional analysis way, and it will come out the same. But again, when most people try to go kind of prefix to prefix, it is super, super common. People screw it up a lot. So it's just safer a lot of times to take it back to that base unit because you can easily find that conversion and then go from that one to the next one and something like that. Just like if you knew how to move the decimal, you could move the decimal. But again, people typically screw it up a lot. Yeah. Yeah. So here's a couple of answers to I think the questions that's being asked is this. You do need to show your work. Okay. So you do need to show your work. And by showing your work, is this dimensional analysis part of what you're supposed to learn and how you show your work? So for here, you do need to show it with this type of setup, with this dimensional analysis sort of setup. Absolutely, you'll get the right answer if you move if you know how to do it properly. Obviously, it'll come out the same. But you do need to show some type of conversion factors used. to solve the problem in this type of setup here. If you know how to do it the other way, then you need to, if you feel more comfortable do it that way. You definitely can, but you still need to show the work. So however it works for you. Once again, in terms of what you would need to show for credit, we're talking basically this setup. So for full credit, that part of it is basically what you need to show. Obviously, with the conversion factors, things set up top and bottom, and proper answer with the right number of significant figures. If it helps you to do all the rest of the stuff, figure out the conversion factors, do it, but you don't necessarily have to show it for work. Let's talk a little bit about significant figures. And once again, this is considered an exact conversion, so you don't have to worry about it. That is also considered an exact conversion, so you do not have to worry about it. That means really the only number we got going on here is the first number. And once again, because of dimensional analysis, we're always multiplying and dividing. We're always looking at sig figs. So that makes that part of it as well pretty simple. You don't have to go, should I do decimals? Should I do sig figs? It's always sig figs on this deal because all you're doing is multiplying and dividing. So that's 4 sig figs, and that's why we do need to keep them all here for 4 sig figs for our answer. Any questions on that there? All right. All right, so we kind of went through some of these, but just to reiterate some of these prefixes, there is 1,000 meters in 1 kilometer. Again, kilos 1,000. That again is the same conversion as obviously kilo is 10 to the 3, and 1 kilometer is 10 to the 3 meters. That's 1 times 10 to the 3. That's 1,000 if you just put it into a regular number. So again, those are all the same numbers basically when you look at it. 1 times 10 to the minus 6 grams is a microgram. And this is what I was saying earlier. We did micro a second ago. The true symbol for micro is that kind of U symbol for micro. But your book kind of bounces between those two things. So sometimes they'll use that symbol, and then sometimes they'll use this for micrograms as well. So just keep that in mind as you kind of go through the book and maybe the online homework as well. They tend to bounce between those two. Maybe whatever page they were using didn't have the symbol to use or when they were making it, but they tend to kind of bounce. But this is truly the symbol most people use for micro, that kind of U with a little extra leg coming out of there. 0.1 liter is deciliters in that case. So we got 0.1 liter is 1 deciliter in those conversions. Again, 1 meter is 100 centimeters is definitely an equality that we use a lot. That also is the same as centi is 10 to the minus 2. 1 centimeter is 10 to the minus 2 meters. And if you divide both sides by 1 times 10 to the minus 2, those guys become 1 meter is 100 centimeters. So there are some conversions or equalities where you can use a kind of a big number if you like, or a more of a non-scientific notation number, and it's perfectly fine. It will come out the same as well, and that's how you get it to those guys. 1 centimeter is 10 millimeters. That's what we see there on a ruler. The little markings on the bottom is millimeters, and the big guys on the bottom of a traditional ruler is a centimeter that has numbers next to it. All right. Here are some volume equalities that we come across a lot. I would say this one for sure. 1 liter is 1,000 milliliters. That's one just you probably should lock away. It's used a lot. Most formulas in chemistry usually will need the volume in liters. And a lot of times when you actually measure volume, say in the lab or something like that, a lot of times it's in milliliters. So that conversion between milliliters and liters is very common. Also, I think we might have talked about it earlier, but 1 cubic centimeter is the same as 1 milliliter, and that is the same as 1 cc, which is also a cubic centimeter. So those are some relationships that we do come across a lot here with volume, as we see on this slide. All right. And I would say definitely, probably these guys we do come across a lot. Kilograms, 1,000. 1 gram is 1,000 milligrams. Again, the base unit doesn't really change. 1 gram is 1,000 milligrams. It's like the same thing as 1 liter is 1,000 milliliters. So that milli conversion, the number's the same regardless of the base unit. All right, so we're looking for which unit is larger here, millimeters or centimeters. There, centimeters. There's 10 millimeters within a centimeter. Sounds good. Kilograms, centigrams, kilograms, deciliters, microliters. Yeah. And again, that's micro. See, even here they went micro and then they went micrograms. Micrograms and milligrams. Milligrams, yeah. Perfect. All right. We're going to continue on. So we sort of jumped ahead a little bit. So we're just going to continue to talk about conversion factors and problem solving dimensional analysis. So as we've been talking about, again, a conversion factor is really just a fraction that comes from an equality. And again, an equality basically represents two different units that represent the same amount of something. So from any equality, as we talked about, you can get two conversion factors from it. By the way, when we're doing those problems like we did previously, and we'll continue to do here, again, as I mentioned earlier, you can get an answer and kind of do each sort of conversion individually. If you do get an answer and do it individually, you do want to make sure you don't round too much until the end. But if you wanted to, and let's say like that two-step conversion we just did, if you wanted to do the first conversion, get an answer, you could do that, then take that answer and do the next conversion. Now, as we've been talking about equalities, which for the most part are considered exact numbers, and really we don't have to worry about those in terms of our calculation and our answer in sig figs. Again, definitely if we are looking at something like we see here, kind of metric to metric, we're all good on that, US to US. But as I mentioned a couple of times, and just a reminder though, if we cross over from metric to US or English conversion, we do need to look at the number of significant figures in that conversion. So for example, if we were using this equality in a calculation, we could get two conversion factors, 2.20 pounds over 1 kilogram, or 1 kilogram, 2.20 pounds. And if we use that in a conversion, we would want to actually look at the significant figures here and take them into account. The number that we would look at in this case is this number. We wouldn't look at the 1. We would just look at like the 2.20, and this would contribute 3 significant figures in our calculation. So remember that although in a lot of cases we could just kind of blow by these equalities and conversion factors, ones that come from metric to metric or English to English conversions, if we are crossing over, you do have to take a moment and look at that conversion factor and see whether or not that's going to be the one that determines how many significant figures your answer should have. I will say probably 98% of the time, it's probably not going to be, but it could be potentially. And you want to make sure you take it into account. Other places where we do get conversion factors that we do have to for sure sort of take into account is if we're given like a conversion factor in a problem itself. Like for example, if you had a problem where it said you were driving 55 miles per hour, that's not a normal conversion. That's not the speed of everybody always, right? That's specific for that particular problem. And if we were going to use that as a conversion factor in our problem, we would have to look at the 55 and the significant figures with that. So if you have any conversion factor that is metric to English, you need to kind of take the sig figs into account. Or if it's any type of conversion factor that's sort of just specific for that problem you're doing and it's kind of given to you in the problem. Any questions on that there? All right. So here we wouldn't have to worry about any of those significant figures because again, they're all considered exact numbers. Here we would have to start looking at some sig figs. So again, we would look at this number in terms of it if we use it in a conversion. We would look at this number if we use it in a conversion, or we would look at this number here in terms of the significant figures if we use it. And again, those are all kind of metric to English kind of crossover conversions, and we would need to kind of take those into account. The one sort of crossover conversion that you do not have to worry about between metric and English is this one right here. Typically, 1 inch is exactly 2.54 centimeters. So because that's an exact conversion, even though it's a metric to English or English to metric, whichever way you're going, you can't ignore it. But all other ones, you do have to kind of take them into account. All right. Here's a table of some common equalities. And again, from every equality on this table, we can get two conversion factors to use in our dimensional analysis problems. Once again, if you are drawing your conversion factor from this table here or that column, you're good. You don't have to worry about sig figs from the conversion factor. If you're drawing from this column here, you do not have to worry about significant figures. If you're taking it from this column here, yes, you do have to look at it except for this one here. So again, that's kind of the column where you do need to take into account those sig figs. Most of these will be provided for you along with the prefixes. So like we were doing those kilo 10 to the 3 and centi 10 to the minus 2, you just need to be able to use them, hopefully. Yeah. So they will probably be provided for you. You just need to be able to obviously properly use them. Yeah. Again, some may not be. So I think we might have talked about it previously, but right, 60 seconds in a minute, right? 60 minutes in an hour. 24 hours only, right, in a day, not 60 hours in a day or anything like that. That's a common one. People do problems. They're like, cool, 60 seconds in a minute, 60 minutes in an hour, 60 hours in a day. There's too many 60s there, so don't go too far. All right. All right, so we kind of touched upon this, so I'm just going to kind of go over these a little bit quicker because obviously we've done some examples. But once again, these are our equalities. And our conversion factors over here, which again is just our fractions. I'll spit that out maybe, I suppose. All right. So taking a look, and again, we came across some of these here previously, but 1 liter is 1,000 milliliters, giving us our two conversion factors, 39.4 inches in a meter. And again, your book kind of going back and forth, but 1 milligram, 1,000 micrograms in that case. Now, as I mentioned before, if you have something given to you in an actual problem, you do need to take the significant figures into account, and you could use it as a conversion factor. So for example, here it says maybe you're driving 85 kilometers per hour. That basically means you're going 85 kilometers over 1 hour, basically. Or you could flip it around, 1 hour, you could travel 85 kilometers. So these are, again, very commonly, conversion factors are actually given to you in the problem. And if they are, again, we would need to take into account here the significant figures when we're doing the calculation. We would be looking at the 85 in this case, which would give us two significant figures, right, in terms of our calculation. So sometimes people gloss over problems when they read it. That sometimes in the actual problem, there's the conversion factor that you probably need to use. So just make sure you read it carefully if you are reading problems. Like here, right, a tablet contains 500 milligrams of vitamin C. That gives us basically two conversion factors. 500 milligrams of vitamin C in one tablet are one tablet over 500 milligrams of vitamin C. So again, these are two conversion factors that we could get from the problem. And in this particular case, we would be looking at the 500. And that 500 is written with how many significant figures here? That is both answers, but we think it is 1 in this case. Those zeros at the end are not significant, right? Because there's no decimal point in the number written. So it would actually have 1. So if you were using this in a problem, it would actually limit, right? Probably your answer. That's probably going to be the one that's going to limit your answer to one significant figure in this case. Which maybe not be bad since you might be calculating how many tablets to give somebody. So you're not like, I'm going to give somebody 1.325 tablets or something like that, right? Percentages is also something else that we see in problems that we can turn into a usable conversion factor. So if you're given a percentage of something and you want to kind of turn it into a usable conversion factor, basically it's good to assume 100 of something, right? And what that does is it keeps the numbers the same. So if you had 50%, on an assignment, you could assume you probably got maybe 50 points out of 100, right? So it keeps the numbers the same, and that's a good way to convert it. So if we have somebody that has 18% body fat by mass, we assume 100 kilograms in this case, and we could do a metric conversion of 18 kilograms of body fat per 100 kilograms of body mass. And just like any conversion factor, we could just flip it. If we want to do more of a US sort of conversion, we could do it in pounds as well, right? We could say 18 pounds of body fat per 100 pounds of body mass, right? So again, unit-wise, it doesn't necessarily matter as long as the numbers kind of stay the same. And again, by assuming you have 100 of something, it just keeps all the numbers the same. Very common as well, right? Doses given in terms of medication. One capsule has 250 milligrams of Keflex. And again, that's going to give us our two conversion factors here. And we would, once again, want to look at the 250 in this case if we needed to use it in a calculation. Again, this is not a standard exact conversion. It happens to be specific for this medication. So it is something that we have to kind of look at in terms of their sig figs. And it would be 2 in this case, the way it is written. All right, let's see here. Let's get into a little bit more problem solving. So we've obviously talked about setting up our things with dimensional analysis, showing the units canceling. And again, it is really the way you want to do it because it does make the calculation relatively easy. It's just all about canceling out the units you don't want, keeping the units you do want. And as I mentioned, basically 3 things you have to remember. Opposites cancel, top multiplies, bottom divides. You're good to go in terms of canceling out things. Once again, as I mentioned before, if you're ending up with 1 unit by itself, it should be up on top. It is possible to end up with 2 units, right? 1 on top and 1 on the bottom. Like, for example, if you went from miles per hour to kilometers per second or something like that, right? So those are just really 2 separate conversions that need to be done kind of on top and bottom to end up in the right location. So if a person weighs 178 pounds, what is their mass in kilograms? So if we were looking at this, we definitely have pounds and we want to end up in kilograms. Now, one of the things about conversion problems is there are multiple ways you could get there depending on what conversions you choose to go there. So there are more than one way that you could kind of get there. For example, one pathway could be going from pounds to grams and grams back to kilograms. So that is one pathway that would get you to what you need. We know from our table there, 453.6 grams is 1 pound. I think on your table, maybe it says 454. That's good too. You can use 454 grams. The other one is a kilo conversion, right? So we do know kilo is 10 to the 3, right? So this is the pathway that can get us here. We again want to set it up like we've been talking about. So the first conversion I'm going to do is take it from pounds to grams. So using my equality here, that's going to give me 2 conversion factors, 453.6 grams over 1 pound. If I write it like a conversion factor, that would probably be good. Or we could flip it around, obviously. 3.6 grams. So I'm going to start my conversion here. I'm going to take the number that was given to me, 178 pounds. Once again, if it helps you, you could put it over 1. So you again could do the top and bottom pretty easily. I would highly recommend you write it like that, not really slanted sort of lines where you're not really sure, what units on top and what's on the bottom, or stacking them or something like that. You want to keep it as clean and as easy as possible so, you get the right conversion. Here we want to get rid of pounds, right? So opposite location, that is this conversion factor right here, where our pounds are in the opposite location. 1 pound on the bottom, 453 grams up on top. Once again, I know for sure I'm multiplying, right? And on the bottom, I am dividing. That's going to get rid of my pounds. And that means if I stop right here, I'm in units of grams, right? That's the only unit that is there up on top. I don't want grams, but I want kilograms, right? So now I could go back to my equality, and I know what that means is in 1 kilogram, there is 10 to the 3 grams. That gives me 2 conversion factors to use for that equality. 1 kilogram over 10 to the 3 grams are 10 to the 3 grams over 1 kilogram. Once again, you could get an answer at this point perfectly fine. Again, I wouldn't round too much here, or you could just continue on with the calculation. I'm going to continue on with the calculation. I can see my grams are on top, which means, should I use the conversion factor on the left or right here? Conversion factor on the up here, which one should I use? She used the one on the left, grams in the opposite location, so they cancel, right? So 10 to the 3 grams and 1 kilogram. I again am still multiplying and dividing. The grams on top and bottom are going to cancel. And I'm going to end up now with kilograms up on top, which is what I'm looking for. I'm going to grab my handy dandy calculator and go 178 times 453.6. That is all the multiplying I'm doing on top. Hit equals. On the bottom here, I really only have 10 to the 3, which is 1 times 10 to the 3, or 1,000, however you want to punch that into your calculator, divided by 10 to the 3, not negative 3, but just regular 3. And that is going to give me on my calculator here 80.7408 kilograms. First off, any question on the setup? Now we need to think about significant figures, right? So first off, we look at our conversion factor there at the end. Do I have to worry about this one in terms of significant figures? I do not. That is a metric to metric conversion. That's an exact number. I do not have to worry about it. How about this one? Yes, that is a metric to English conversion. I should look at which number there? Yeah, 453.6, which is how many significant figures? It is 4. By the way, if you use 454, you would have 3 significant figures in that case, right? I should also look at the original number, which has 3 significant figures. Because this is dimensional analysis, the only type of math I'm doing is multiplying and dividing, which means my answer should end up where? How many significant figures? Should end up at 3. That would take me here. So like an 80.7 kilograms, yeah? Would end me at 3 significant figures based off of that original number. Any questions on that there? Yeah. Absolutely. I mean, there is, like I said, multiple ways depending on which ones you grab. Like I said before, that is one way you could do it. If you could find a direct conversion, should give you pretty much the same answer. Yeah. Definitely with conversion problems, there are multiple pathways depending on which sort of conversion you kind of pick up and go with. But if they're all legit conversions, they all should give you pretty much the same answer at the end. Maybe slightly different with some rounding and stuff like that, but it should be very, fairly close. Yeah. Other questions? All right. And as you can see here, they did use, as you asked, they used a more direct conversion, which is 1 kilogram is 2.2 pounds. And you can see they pretty much got the same answer, right? A little bit different because they used a slightly different conversion, but perfectly fine. So definitely with conversion problems, there are multiple pathways depending on sort of which one that you look at. All right, so why don't you try this one? A rattlesnake is 2.44 meters long. How many centimeters is the snake? 2 centimeters, right? So again, depending on sort of what you want to do, maybe the centi is the move. You look on your little chart for centi, and it says 10 to the minus 2, which means that in 1 centimeter, there will be 10 to the minus 2 meters. By the way, again, that is the same as 100 centimeters is 1 meter. So again, you could also use that conversion if you like, maybe the whole number there rather than the scientific notation number will come out the same. That again is going to give us some conversion factors. 100 centimeters, meter over 100 centimeters. And we're going to start and set it up. So 2.44 meters. Again, if you want, you don't have to, but if it helps you put it over 1. Clearly, I can see meters are up on top and I want to get rid of them. So opposite location to cancel, that is what we're looking for. And divide. That meters are going to cancel, going to leave the centimeters up there on top. So that is a 244, 2.44 times 100, which is 244 in this particular case. In terms of significant figures, metric to metric, so I do not have to worry about it. Original number here, 3 significant figures. Answer 3 significant figures in this case, yeah. Once again, still multiplying the top, dividing the bottom. You should get the same answer if you use 1 centimeter over 10 to the minus 2 meters and so forth if you use that conversion as well. Any questions on that one there? Yeah. You you can use if you said 1 centimeter is 0.01 meters. Is that what you said? Yeah, it's the same. It's that's the same as the 10 to the minus 2, just in decimal form. So it should work fine. It would be set up similar in terms of where the units would be, and then obviously put the number in the proper location. Yeah. Other questions? All right. Uh, all right. So again, as we talked about, there are sometimes multiple steps along the way. So if we take a look at this one here, a doctor ordered a doses of 0.15 milligrams. If you have 50 microgram tablets in stock, I feel like I killed the fan. That's not really good. Still going, so that's a good sign, I suppose. We want to know how many tablets we want to give. So why don't you give it a go and see as I pick the fan off the floor. Yeah, bad that out. So again, a reminder that your book likes to use this for micrograms. Yeah, so that was the same as we saw earlier, that kind of symbol. Yeah. Okay, let's talk through this one here and find somewhere I can write. Maybe we got 100. What we got there? 0.15 at 50. So we basically have from this problem 0.150 that was milligrams, right, is what we want to give the patient, right? We have our medicine supplied as 50 micrograms per tablet, right, or capsule. I'll go with tablet, it's kind of the same idea. Right. So in this particular problem, we want to know how many tablets to give the person, right? And we basically have an equality or conversion factor given to us in the problem, right? And that is basically the pill, right, how it comes. So that's basically a conversion factor that we could get, micrograms per tablet or capsule, or we could flip it around. One tablet is 50 micrograms. So that doses is how the medicine comes, is what's going to allow us to basically convert from the doses we need to give them to how many tablets we should give them, basically, right? The problem that we have, though, is when we look at our conversion factor that we got from our problem here, it is in micrograms, while our doses here is in milligrams. So we cannot use these things together the way they are written until we do a conversion to get those grams units, if you will, into the same unit. It really doesn't matter which way you want to go. If you want to take the milligrams to micrograms, you could do that. You could also convert the micrograms of the tablet into milligrams. They both really should give you the same answer. It doesn't really matter. I'm going to choose to take the milligram doses and turn it into micrograms. So the first conversion I want to do is take this to micrograms. That way I could actually use the conversion factors that are in the problem. And we just want to think about this as just a regular conversion, right? So if I had milligrams and I want to get to micrograms, once again, I'm going to take the safe route and take it to grams first, right? And then take it to the next prefix. So this is sort of the pathway that's going to get me to micrograms here at the end. And now I will be able to use my conversion factor when I do that. So we know that milli, right, is 10 to the minus 3. Micro, as we saw earlier, is 10 to the minus 6, I believe. So we're going to start with my 0.15 milligrams. And I'm going to use my milli conversion here. And again, that means in 1 milligram, there is 10 to the minus 3 grams. You could also use 1,000 milligrams is 1 gram as well. It's the same thing. So if you want to use kind of the bigger number, you can. That's going to give me two conversion factors, obviously, to use. 1 milligram over 10 to the minus 3 grams, or 10 to the minus 3 grams over 1 milligram. So starting my conversion here, again, if I put it over 1, that should make my decision pretty easy. Opposite location to cancel, right? So milligrams are on top. I need milligrams on the bottom. 1 milligram is 10 to the minus 3 grams. Again, I'm always multiplying the top, dividing the bottom. If I stop right at this moment, what units am I in? Grams. The milligrams will cancel. I am in grams, right? I do need to go one more, right? I need to take it now from grams to micrograms using our micro conversion. And that means in 1 microgram, there is 10 to the minus 6 grams. That is going to give us, again, our two conversion factors we could use. 1 microgram over 10 to the minus 6 grams, or 10 to the minus 6 grams over 1 microgram. Still setting it up with my dimensional analysis. Grams are on top at this point. I need grams on the bottom, which means I need to use the conversion factor like so. And that's going to put 10 to the minus 6 grams on the bottom, 1 microgram on top. Still multiplying the top, still dividing the bottom. Grams on top and bottom are going to cancel. That will now turn my units into micrograms. And the reason, again, I'm doing that is my conversion factor in the problem's in micrograms. So they got to be in the same units to use them together. I'm going to take 0.15, going to multiply it by 1 times 10 to the minus 3 and hit equals. I'm going to divide it by 1 times 10 to the minus 6, which is on the bottom. And that's going to give me $1.50 here, micrograms. First off, any questions so far on that part of the conversion? The whole purpose of this conversion is to get that number into the proper units so that I could use the conversion factor in the problem with it. Any questions up to there? At this point, I can now use the conversion factor from the problem. And it is still dimensional analysis at this point. So if it helps you, pop a 1 over that. And now I can see my micrograms are on top or bottom here. Micrograms are on top. I want to get rid of micrograms, which means they need to go on the bottom. So that's going to be this conversion here, where 1 tablet is 50 micrograms. Still multiplying the top, dividing the bottom, micrograms cancel, tells me how many tablets I should give this person, perhaps 3. Tablets or caplets, I can't remember what it was, capsules, one of those things would probably be the right one. First off, any questions on that there? Let's talk sig figs, right? We do not have to worry about it here. We really don't have to worry about it here. Here we do have to worry about it. That is 3 significant figures. Do I need to worry about the significant figures in this conversion? I do. It came from the problem, right? So that is specific for this problem. I would look at this number, which has how many significant figures? 2. That means my answer should end up with 2 significant figures, yeah? Based on that last conversion that came from the problem in this case. Again, by doing a dimensional analysis, you're always multiplying and dividing, so it's always significant figures you're looking at. So that's keeps, again, that simple. Any questions on that? This is a very common type of situation where you're kind of given a conversion factor in the problem and you have some other number, but they're not in the same unit. So they always have to be in the same unit for that conversion factor to work with it. They cannot be in different units. Otherwise, you will be off, obviously, by a factor or whatever it is that you're multiplying. Any questions on that there? Yeah. Yeah, so it's basically something more of an exact. So I would say typically when you got a conversion factor that you have to take into account, a lot of times there'll be one of the numbers will be 1, and you usually can just ignore that number and then go with the other number that's not 1 is in most cases. Yeah. Other questions? But yeah, also because if you had so many tablets or pills, right, you would just count how many you have, obviously. Yeah. Other questions? All right. We got that, I think. How about this one? Your pace on the treadmill is 65 meters per minute. How many minutes is going to take you to walk 7.5 kilometers? So give it a go. Again, kilo 10 to the 3. Okay, so if we pull out the information, once again, we are given a conversion factor here. We are moving at 65 meters per minute, and we could use that as 65 meters over a minute, or we could flip it around and use a minute is 65 meters. We're going a total distance of 7.5 kilometers, and we want to know how many minutes. This is really a rate, right? It is distance per time. How fast you're moving, like when you're driving, right? How many miles you could go in an hour, all that good stuff. And this is a distance. Once again, we have a similar problem, which is this unit of distance is different than that unit of distance in my conversion factor. So we cannot use them together until we get both of those distance units or length units into the same unit of measurement. Once again, you could convert the meters to kilometers or the kilometers to meters. It's your choice. I'm going to convert the kilometers to meters using my kilo conversion. So I got 7.5 kilometers. I once again know that in 1 kilometer, that is 10 to the 3 meters. So I'm going to use that equality to give me my conversion factor. Opposites are going to cancel, so kilometers are on top. So my 1 kilometer should go on the bottom. My meters should go up on top. Just like normal, we are multiplying and dividing. Kilometers will cancel. We're going to go 7.5 times 10 to the 3. Going to give us 7,500 meters. That is now good because I could use that with my conversion factor that's in meters. And we're going to set up another dimensional analysis here. 7,500 meters. Once again, opposites cancel. So meters are on top. I need meters in the opposite location. That is as much thought as you maybe should give to it. Yeah, just go opposites always here. So we're going to go 65 meters on the bottom, a minute up on top, and we're going to still multiply and divide always. Meters are going to cancel. In this case, we're basically taking 7,500 and dividing it by 65. That's going to give me a lot of numbers. 115.3846154 minutes. I'm feeling like that is too many significant figures. I hope you should feel that too, yes? So you don't feel a big X on that answer when you give it to me. So here we want to look at what we did. First off, right, we go back to our original calculation over here. This we do not have to worry about, right? This number we do, which has 2 significant figures, which means this guy should have 2 significant figures, which it is, that's the way I wrote it, but just in case it didn't, that is how many it should have. Now I come over here where that should have 2 significant figures. Do I need to worry about this number over here, this conversion factor? I do need to worry about it, right? Because it's specific for this problem. That is 2 significant figures, which means my answer should end up in 2 significant figures right about there. That is a 5 next door to it, which means I need to round up. So it's a $1.20 minute. Yeah, 120 minutes. A little jaunt, yes. Any questions on that there? So it's really important. Sometimes people try to do conversions and the units aren't the same. So they always got to be the same to cancel. And again, opposites cancel as well. All right. All right, let's try one more here to finish up on. You go to the local AM PM, you grab yourself 32 fluid ounces at the Thirst Oasis. Crushed ice, cubed ice, everybody goes crushed, right? Is it even a question, right? It's crushed ice. We want to know how many gallons of Diet Coke did you drink? Here are some equalities and some conversion factors that might be helpful. Set it up, see what you come up with. Yeah. On the previous one? Yeah. Are you asking how did we get to 120 from this answer? So based on the calculation we did, we had to get 2 significant figures. So when we look at the answer that was on our calculator, the second significant figure would be this 1. So now we have to look at the number next to it, which is a 5. And that means we have to round up, right? And we round up that 1 to a 2 in this case. And we still need the 0, right? So we don't change the meaning of the number. So we can't just write 12 because that's very different than 115, right? So we need to round it up to 120 in this case. No decimal on this number, otherwise we would have 3 significant figures, yeah? So it's based on rounding up, and that's the number next to where we want to end. Would it be what? It would not be 126, no, because this right here is the second significant figure, and that's where we need to end. So we only look at this number to determine where we should do. Should we round up or drop a number or put a zero? And in this case, because it's 5, we round that 1 to a 2, and that's the proper rounding at 120.